Hello everybody and welcome back to another brainstorm. So today we're going to be looking at the topic of motion in preparation for your GCSE physics exam. So I've split this topic up into three main parts. So for your exam you need to be comfortable with analysing both distance time graphs and velocity time graphs, and we'll explain those later in the video. And then we'll also take a look at the topic of acceleration and how we apply that to some maths type questions, looking specifically at these SUVAT equations for the exam. So let's get into it. Okay, so now we're going to take a look at distance time graphs. So just take a look at this graph for me. This is one that might come up in your exam, something like this. And as the name suggests, you can see that a distance time graph plots an object in motion, and it tells us how far the object has travelled, i.e. its distance across the y-axis, over a given time, i.e. its time on the x-axis. You need to be able to understand these graphs, interpret them, make statements about them, and we're going to look at that now. The first thing that you need to know is this equation here. This is probably the most important equation you're going to learn in your physics. Speed equals distance over time. Pay attention to the units here as well. Our distance is measured in meters, time is in seconds, and speed is meters per second. In your exam, you might see that as m over s as well. Now, you might have inferred from the graph that because speed is distance over time, the speed is the gradient of our graph. So for this graph here, we see how far has it travelled in its journey. So we've got the distance, i.e. the rise of the graph, and that's 6,000 meters. And it's travelled that over the run of the graph in 240 seconds. We can plug that into our equation here, and we can say that the speed of this object is therefore 6,000 over 240, and that comes out to be 25 meters per second. And that's a really quick calculation that you need to be able to do in your exam. Now, consider that speed is the gradient of the graph. Something like this, you can see that the gradient isn't changing no matter where we look, and so therefore the speed isn't changing either. For a graph like this, we say that the object is travelling at a constant speed. I'll just write constant up here. But that's not what always the distance time graph is going to look like. It could look something like this. Now for this one, let's say that this is at 2,000 meters, and we've got 0, 1, 2, 3, 4 seconds. Now what you'll notice is whatever object this is, it's staying at 2,000 meters for 4 seconds. It's not moving anywhere. And because of that, because our gradient's 0 as well, we say that speed is 0. And because it's not moving, we can say that this object is stationary. That's a very useful word to use in the exam. Now something a little bit more complicated might look like this. Now this is again a distance over time graph, but this time you'll notice that although the graph is going up, the gradient isn't staying the same. The gradient here is not the same as the gradient here, and that's not the same as here. And because the gradient's increasing, our speed is also increasing. And as you'll know, the increase of speed is called acceleration. So for an object where the graph looks like this, we say it's accelerating. Now a skill that you need to have for your exam is you need to be able to find the speed at a given time. Let's say we've got 1, 2, 3, 4 seconds here. The exam question might ask you, can you find the speed of this object at 3 seconds? And for that we have to draw a tangent. Now a tangent is a line that we draw that touches the curve only at one point. In our case, because the question's asked us at 3 seconds, we draw the tangent at 3 seconds as well. And then simply you just find the gradient of that tangent to find your speed. Now, as well as interpreting these graphs, you need to be able to compare different objects in motion. Like I said before, the steeper the gradient, the faster the speed. So for this, you need to make statements here, like x is faster than y, for example, or you need to be able to spot that z, for example, has stayed stationary for 500 seconds. So watch out for that in your graphs. Okay, so now we're going to look at the concept of acceleration and our SUVAT equations. So before we actually get into acceleration, we need to get comfortable with this idea of velocity. Now you might have heard of that word before, but velocity is the speed of an object, but it's in a given direction. Now as you'll know from your previous physics, velocity is therefore a vector quantity, which means that not only does it have a magnitude, i.e. it tells us how big the force is, for example, or how fast we're traveling in this case, but it also tells us in what direction that is. So it's a bit different to speed. Speed only tells us how fast, but velocity tells us how fast and also in what direction. That's a concept you need to get your head around, because a very typical exam question is, an object is travelling around a roundabout or in circular motion. It's travelling at a constant speed. So let's say this car is going around a roundabout at 10 meters per second, and that doesn't change. Although it's travelling at the same speed, the velocity is constantly changing. Explain why. Now in that exam, you need to say that velocity is a vector quantity, so it takes into account not only the speed of this car, 10 meters per second, but also the direction. Now because this car is going in a circle, its direction is constantly changing over the journey, so the velocity is always changing as well. So moving on to acceleration now. Acceleration is the rate of change of velocity per second, so how fast does that velocity change? So this is a very important equation that you need to get your head around as well, you'll be using this a lot. Acceleration in meters per second squared, notice that, and it might be seen as this as well, m over s squared, is equal to change in velocity. Now this is a delta, it just means the change in meters per second, we've already covered that, over time in seconds. Now what we mean by change in velocity is you take the final velocity, so what speed does the thing end up in, and the initial velocity, and just find the difference there. So for example, if a car started off at 6 meters per second and it sped up to 8 meters per second, our change in velocity is 2 meters per second. And moving on from that, we look at these SUVAT equations, and that puts everything together. Now for these, I recommend you just pause the video and learn all of these equations. The better you know them, the faster you'll be in the exam, and that's saving valuable time. Pay attention to the letters as well. U is the initial velocity, V is the final velocity. Now I'm going to do one practice question to show you how you'd be applying this in the exam, and I would actually say that this is one of the harder questions that you'll see. So a car is moving at a velocity of 28 meters per second. It then brakes and it stops in 8 seconds. Calculate its deceleration. Now deceleration is essentially exactly the same as acceleration, but instead of speeding up, it's slowing down. So we say this is negative acceleration. So a car is moving at a velocity of 28 meters per second. Well, that's our initial velocity. And for the SUVAT equations, we say that is the letter U. And we said it stops, so we assume that it finishes at 0 meters per second. That's our final velocity, and we call that V for the SUVAT equation. And it does all of that in 8 seconds, that's our time, T. And we need to find our deceleration, which is a form of acceleration, and we say that is A. So the first step for any maths question in physics is we write out the information we have. Initial velocity U is equal to 28, final velocity V is equal to 0, the time it does that in is 8 seconds, and then we're trying to find acceleration, which we don't know. Now if we go over here, the equation that uses all of those letters is V is equal to U plus AT. So we write out our equation as always, and then we just plug in those numbers where appropriate. So V is 0 is equal to U 28 plus A, which we don't know, times by T 8. So we say that 0 is equal to 28 plus 8A. Now this is just a little bit of simple algebra, which you'll have to do here. So you take the 8A to the other side, negative 8A is equal to 28, and then as you know, you do 28 divided by negative 8, and in your exam you're not expected to do these in your head, you'll be able to use a calculator, but in this case the acceleration is negative 3.5. But because the question specifies that we're talking about deceleration, we don't need to worry about the sign in front, so we just say therefore we've got a deceleration of 3.5, and never forget your units, meters per second squared. Okay, so we're going to finish by taking a look at velocity time graphs. Now these are a little bit more complicated than distance time graphs, but it's not too bad. So for a velocity time graph, as the name suggests, again, we're plotting an object's velocity, i.e. its speed in a given direction, over the time on the x-axis, and these should have our units, but we don't. Okay, so for an object moving, you'll see if it is at rest, its velocity is going to be 0. That's the whole point of it being at rest. It's not having any speed. So if an object is stationary, it's going to stay at 0. If an object is constantly accelerating, its velocity is going to be increasing at a steady rate. So if you see it going up like that, that's a constant acceleration. Now let's say that this is at 5 meters per second, for example, and it's traveling at that for some time. We say that that object is traveling at a constant velocity. So over this period of time, it could be 5 seconds. For that whole 5 seconds, our car, for example, might be traveling at 5 meters per second with no change. Now, if the velocity decreases, like we've said before, that's called a constant deceleration. Now you'll notice that what's a little bit different here is that the gradient, instead of representing the speed, represents the acceleration. So how fast does that velocity change? So if you're asked to find the acceleration, you just do your change in velocity, which is our rise, over the time it occurs. There. Another concept that you need to be quite familiar with is how to find distance using the velocity time graph. And you just need to remember this fact that the displacement or the distance travelled is the area underneath the curve. Now luckily at GCSE level, your curve on a velocity time graph is usually going to be a nice shape. It's either going to be made up of squares or triangles, and you'll know from your maths that the area of a square or rectangle is length times width, and the area of a triangle is half base height. So if we take a look at this velocity time graph, for example, and it said to us, how far does the car travel over the 15 seconds? Well, how far? It's asking us for the distance. So we're going to try and find the area of this coloured in region. So we split it up into normal shapes, our rectangle and our triangle here. So the area of this yellow rectangle is going to be 10 seconds times by our 20 meters per second, and that's 200 meters. And then for our triangle here, we're going to do half times the base here, which is 5. So half times 5 times the height times 20, and that's 50 meters. So if we're asked for the total distance, we just do 200 plus 50, and then this car has traveled 250 meters. And that's about as hard as the velocity time graph will get. And with that, I'd just like to say thank you guys for watching. Please make sure to hit like and subscribe, and I'll see you guys soon.